Okay, number 12, looking at the Q calculation problem for review. First things first, you need to be able to recognize these ones, and how you recognize these ones if you're given initial concentrations for all the chemical species. So you're given all the concentrations or partial pressures initially. There are no non-zero ones. I mean, all of them are non-zero. There aren't any that are zero. We won't know which way it's proceeding to reach equilibrium without figuring out the Q value to begin with. So we have to know the initial, do a Q calculation and compare that to K, so we know which direction the reaction proceeds to get to equilibrium. Very important there. So recognize these because you have initial concentrations for all of the chemical species, or initial partial pressures of all the chemical species. So now take a moment to read this, set up your rice table. And what you should notice, as you can see, we have initial concentration of hydrogen is 1 molar, the initial concentration of nitrogen is 0.5, and the initial concentration of the ammonia happens to be 5 molar. So take a moment to do the Q calculation, and then we will look at it. Okay, so we set up our Q calculation, which is the same as using the law of mass action, which is what you would use to find K. So the ammonia squared over the hydrogen cubed times the nitrogen concentration on the bottom. When you insert the numbers, you should get a Q value of 50. Did everybody get a Q value of 50? All right, so we see here that Q is greater than K, so the reaction proceeds towards the reactants. So we can appropriately finish filling out our race table to go the correct direction. All right, so let's do that. You know we're going left towards the reactant, so this is going to be minus 2x. This is going to be plus x. And this is going to be plus 3x. Then we fill the rest in here. 1 plus 3x. 0.50 plus x. 5 minus 2x. Seeing this representation here, knowing we have our K value right here, how are we going to solve? How are we going to find x? What do we need to do? Graph it, yes. Or you're welcome to use the quadratic formula. I don't recommend, though, it takes too long. So we're going to stick it in the expression, like so, and graph it. So take a moment to graph it. Make sure that you get the right intersection. Yes, what did we get for x? What do we got for x? 0.195. Did you get that?
My graph is broken on my calculator.
Oh, okay. Well, we'll have to see what we can do about helping your graph. Yeah, I can mistype stuff in the calculator all the time. So just try to make sure that you put it in accurately and work on those graphing skills because you need them here. Now all you have to do is plug them in to the equilibrium concentrations highlighted at the bottom row in yellow. And then we can find the equilibrium concentrations of all the chemical species, the H2, the N2, and the NH3. Yes? There you have it. So here are our concentrations. 4.6 molar, did you get that? For ammonia. 1.6 for hydrogen. And 0.70 for nitrogen. Yes, no, maybe so? Close enough? All right, good to go. Multiple choice questions. Woohoo! My favorite. Multiple choice questions. There's a lot going on here, so give yourself like a minute to read it. Diagram above. So they gave us a particular model diagram here. Important to note. They tell you the size of the container. They tell you the reaction. And what must be true about the value of the equilibrium constant. So what do we need to do here? Any ideas? What's the first thing we should do here?
Set up like the parts of reactions.
Count, yes. Okay, we need to figure out, because in order to calculate K, you need to either have a concentration or a partial pressure value. They gave us particles in a 1 liter container. Can we figure out the concentration? Yes, we can. We count them. Exactly right. So, 1, 2, 3, 4, 5, 6. We have 6 of those. And 1, 2, 3. We have 3 of those. Very good. And it's out of 1 liter, so we know that's virtually the same thing as the concentration, right? There we go. Yes, and now we need the expression, but this is a multiple choice question. Do you want to waste your time writing out the expression? No, you can just plug and chug, right? Okay. So here we have the product. Which one's the product? 3. So we put 3 over our reactant, which happens to be 6. Don't forget the squared here. Square it. Now, we got to do the mental math because, right, you're not allowed to use your calculator on this. So, really, what is this?
1 over 12.
This is 3 over 36, which is 1 over 12. Very good. Something small. Exactly right. So, K is obviously not 0. Duh. 1 over 12. K is not equal to 1. K is not greater than 1. So it has to be B. Exactly right. So that's the kind of numbers that they're expecting you to be able to deal with in your head.
Wait, miss that.
Yeah.
That one? Like, could we just use the number of moles that are like in the equation? So do like 1 over 2 squared? Because that would give us 1 over 4. And technically that still gives us answer B. You know what I'm saying?
Yeah,
Like instead of using the picture.
but they want you to use the picture. That's why they put it there.
Okay.
Just letting you know, yeah. So technically that does work, but they want you to, but what if they didn't give you the exact same ratio there? What if they gave you different numbers?
Yeah.
Okay? She was asking about the, like, calculating it without using the picture. And the way she was doing it works in this particular case, but it wouldn't necessarily work if they gave us different ratios in the picture. So say, the NO2 was 3 and the N2O2 was 6. So you do have to use the picture is what I'm saying. Okay? All right. B is correct. Moving on. All right, here you go. 445 degrees Celsius, Kc is 0.02. Mixture of H2I2 and HI in the vessel has the following concentrations. Which of one of the following statements concerning the reaction quotient Q is true for the above system? All right, so we need to calculate Q here because we won't be able to tell and compare it to K until we have that value. So once again, this is multiple choice where you don't want to waste time. So I would just stick with I2. Where's I2? Okay, that goes on the top of the expression. H2, 0.5, that goes on the top of the expression. And HI, that's your reactant, so that goes on the bottom. And that is squared because of the 2. Now, This is that decimal math I warned you about that you're supposed to be able to do in your head. This is how I do it. I'm going to show you. What's 0.1 times 0.5? 0.1 times 0.5. 0.05. Okay, good. All right. 2 squared is 4, right? Okay, that's a headache for me, and I don't like to work with that. So this is what I do. I do 5 over 4 is 1.25. Can we agree on that? So far, so good. You see, I just shifted it 2 decimal places, right? So then all I have to do to fix it, you know, because these 2 decimal places is go 1, 2. So 0.0125. There's my answer. That happens to be Q. So, in that case, Q is less than K, right? Because K is 0.02. Right? So that completely gets rid of A, that gets rid of D, that gets rid of E. I don't have to bother reading them, right? Because we know Q is less than K. Which way is it shifting though? To get to equilibrium? Or which way is it proceeding?
Towards the products.
Towards the products. So here, definitely B. Okay, this is a fun-filled one for Le Chatelier's principle. And they kind of take everything and throw it into one question. So, consider the gas phase equilibrium system presented by the equation. Given that the forward reaction is endothermic, which of the following changes will decrease the equilibrium amount of the water vapor? I see endothermic. What do I immediately do? What do I do with my heat? Correct. First things first, gotta do that. So now, as it presents the scenarios to me, I can think about it. Now let's think about it. Adding more oxygen. Which way is that gonna go?
Towards the reactants.
This way, right? So that's actually gonna make more water. So that's a no, right? Adding a solid phase catalyst. What happens with the adding a catalyst?
Speeds.
No effect.
It shouldn't do anything because
Yes, it's no change, does not affect the position, it just speeds up the reaction in both directions. So this is the no change one. That one's done. Decreasing the volume of the container, which means the total pressure is increasing. How do we figure that one out? What do we need to count? Number of moles. This side has 2 moles of gas. This side has 2 moles plus 1 mole. So that's a total of 3 moles of gas. When we increase pressure, which side do we go to? So go to the side with more moles of gas or less moles of gas? To the side with less moles of gas. Exactly. So that means it's going left towards the reactants, which would also increase the water, right? No, bad. We want to decrease the water. How about increasing the temperature? Increasing temperature is like adding in heat. Which way is that going to go? Increasing the heat, which way are we going to shift? This is endothermic.
Towards the products.
Yes, this one's going to go right towards the products. Remember heat, we're adding this here. Going to go that way. Is that going to decrease the water amount?
Yes.
Water vapor amount, yes. So I'm going with D for right now. But I'm just going to scan just the other answer just to make sure, but it says adding helium gas.
No.
What's wrong with that one?
It's
isn't it?
inert.
Yeah, inert's the reactive. So.
Inert gas is a no. right? No change on the inert gas. Sure, go ahead. Can I explain which one again? Okay, since this is endothermic and heat is located on the reactant side, if we're adding in heat, we're adding to the reactant side, it shifts right towards the products. That means the water vapor gets consumed and it decreases. Thank you. It's been years of practice. I can't do that, sorry. All right, take a moment to read this scenario. Give you okay, this is for numbers 4 and 5. And sometimes in the multiple choice section, they will have you reference the same scenario for 3 questions. So in this case, we're just going to have 2 questions with it, but we have the water vapor decomposing into hydrogen and oxygen. They tell us the initial partial pressure when there's only water vapor in there is at 2 atm. Over here, this is at equilibrium after it's gotten established. We have water vapor, hydrogen, and oxygen, and our total pressure is now 2.50 atm. These are the points that you need to make sure you are paying attention to. Okay, so here, which of the following statements about Kp, the equilibrium constant for the reaction, is correct? We need to find Kp. So what do we need to set up in order to find Kp? And we have initial, and then we have total pressure at the end here. What should I set up? Rice. Rice is nice. Let's set up a rice table. Let's go. Initially, we have 2 atm here, and 0, and 0. So we have initially. Which way is it going to proceed? Right towards the products, right? Because we have 0 products to begin with. So we know it's going that direction. So this is minus 2x, this is plus 2x, and this is plus x. All right, so that means we have 2 minus 2x plus 2x plus x here. Now, quick question. What do we know about, in here, we have a gas mixture. 3 separate gases in there, and the total pressure equals 2.5. Any gas laws that we think of that have to do with gas mixtures with total pressures? Does have something to do with partial pressures. Yes, Dalton's law of partial pressures. Everybody remember that one? Guess what? Dalton's law of partial pressures. You can use this here because the total pressure should equal the partial pressure of all the components in there. And guess what? This plus this plus this. We just add these together and guess what? They should equal the 2.5. And nicely done here. Guess what? We have minus 2x and we have plus 2x. So those cancel. So technically we have 2 plus x gives us 2.5. Can we find out what x is? 0.5. 0.5. So this one, they're asking you to apply Dalton's law of partial pressure to get the answer there. Now that we have this, we can figure out our equilibrium partial pressures. So here, for this one, 2 minus 2 times 0.5, that's going to be a 1, right? 2 times 0.5 here, that's also going to be a 1. And this one's just 0.5. Can we figure out Kp now? Hopefully that's a yes. We can figure out Kp. Let's do that. So we have 0.5 times 1 squared over 1 squared. So what is Kp? 0.5. So which one does that fall into? B. It is less than 1. So apply Dalton's law of partial pressures. Yes, it works here. This is the last little one that I can think of that's different than any of the other problems. B is the correct answer. Aha, next one. Throwing in a different concept with the same scenario here. And yes, this one you might have to go back and reference and think about some of your gas law stuff, since we're talking about gases here. Which of the following is the most likely cause for the increase in pressure observed in the container as the reaction reaches equilibrium? Well, let's look at A. Let's just start going through them. A decrease in strength of intermolecular attractions among molecules in the flask. B, an increase in the strength of intermolecular attractions among the molecules in the flask. Both of those have to do with intermolecular attractions. What do we know about gases in a container when we're thinking about the kinetic molecular theory? What is the assumption about gases? There are no forces. No repulsive, no attractive forces. So, A and B, we're just going to throw out. See you later. We're assuming no forces. They're not telling us it's deviating from ideal gas law or anything here, so those are out. Now looking at the last two, we have an increase in the number of molecules, which increases the frequency of collisions with the walls of the container, or we have an increase in the speed of the molecules that then collide with the walls of the container with the greater force. Anybody like to state an answer to support? You think C? I think C is correct too. Now why is C correct?
Because you have more molecules.
Having more molecules, how can I tell that I have more molecules?
Because it states it. With H2 or the nitrogen oxygen gas.
What gives me evidence that there's more molecules in there? The total, yes, we went from 2 ATM to 2.5 ATM. What is something also that has been kept the same?
Volume.
Volume is the same, but what else has been kept the same here?
Temperature?
Temperature is the same. Temperature has not been altered. So, would the molecules be speeding up? Would they have greater average kinetic energy? No. So D doesn't really make sense because the temperature hasn't been changed.
Yeah.
What happened though, as you can see, is the water, some of it decomposed. And essentially what's going on there, some of it that decomposes, it goes from 2 moles to 3 moles. So you know you're creating more moles when you create products. So therefore, there must be more particles in there, more molecules hitting the walls of the container. The only way D would work is if the temperature had been increased. So C is the correct answer. Right? We agree on that? All right, last question. And this is one I threw in there because we always like to forget it, and so many people miss this all the time. And it's sort of like one of those, oh yeah, duh, oh, I should have remembered that. So take a moment to read it. And remember what you remember about K here. Following statements made about K, equilibrium constant. What say you? What do you think? All right, so I have 2 for C now. What do we know about the equilibrium constant? That the only thing that can alter it and make K a different value is changing temperature. Yeah, exactly right. And we always forget this. We always forget that K, the only thing that alters K is temperature. And they always throw it in there as a question. So try not to forget that one. So remember, you can add products, add reactants, and yes, the products and reactants amounts are going to change, but it gets back to that proportion value of products over reactants. So the K value itself does not change. The reactants and products amounts do. The concentrations are partial pressures, but the proportion following law of mass action does not change. And there we have it.